Bismillah ar-Rahman ar-Rahim. Starting with the gracious name of Allah, who is ar-Rahman and ar-Rahim. Assalamu alaikum everyone. Myself is Ilyas and I am the student of MS Chemistry Batch 5. The topic I am going to present today is overview of the plug flow reactors, fluidized bed reactors and packed bed reactors. And I am representing this article to Dr. Hamad Majid. First of all, I will show you the contents of my article. The topics I have been covered in my articles are introduction and abstracts of all of these reactors, their definitions, key characteristics, design and working principle, their residence time distribution, their types, components, and their applications in the chemical industries, then the merits and demerits of all of these reactors, their case studies. And in the last, I will tell you about the conclusion of all of these reactors. Moving toward the article, first of all, I will tell you about the introduction to chemical reactors. And this, we will see basically what are chemical reactors and why we use chemical reactors in chemical industries. Chemical reactors constitute an integral component in the field of chemical engineering, providing controlled environments where chemical reactions occur to convert raw materials into desired end products. These reactors, crucial across diverse industries such as pharmaceuticals and petrochemicals, are chosen based on the factors like reaction kinetics, temperature, pressure, and the nature of reactants and products. The classification of chemical reactors involves various types, including batch reactors, continuous state tank reactors, and plug flow reactors, each tailored to specific reaction conditions. Now, I will tell you about the abstracts of all of these reactors. First of all, there is plug flow reactors. Plug flow reactors stand out as a crucial category within chemical reactors, distinguished by their continuous flow of reactants through the reactor, maintaining a concentration gradient along its length, unlike well-mixed systems. The significance of plug flow reactors in chemical engineering arises from their capacity to provide precise control over reactions condition. This is particularly advantageous in situations where strict temperature profiles or specific residence time distributions are paramount. In various industries, plug flow reactors play a vital role in ensuring optimal efficiency and control for chemical transformation. The second one is fluidized bed reactors. Fluidized bed reactors stand as a significant progression in chemical engineering, providing a dynamic and adaptable approach to a variety of industrial applications. In these reactors, a bed of solid particles mobilized by the upward flow of gas or liquid taken on a fluid-like state. This distinctive fluidized conditions enhances heat and mass transfer, rendering FBRs crucial for catalytic reactions, combustion processes, and diverse chemical applications. The key characteristic of fluidized bed reactors lies in their ability to sustain continuous particle motion, offering advantages like improving mixing, consistent temperature distribution, and heightened reaction rates. This dynamic behavior proves particularly beneficial for processes demanding precise control over reaction conditions and efficient catalyst utilization. Fluidized bed reactors find widespread use across industries, including petroleum refining, petrochemicals, pharmaceuticals, environmental management, and bioenergy. And the third one reactor is packed bed reactors. Packed bed reactors are integral chemical reactions extensively used in industry. The feature a cylindrical chamber filled with solid particles or catalysts, enabling fluid flow for chemical reactions. This introduction explored the foundational principles, structural components, and the importance of packed bed reactors across various applications, highlighting their capacity for substantial surface area, facilitating effective mass transfer, and supporting continuous operations lays for the groundwork for thorough comprehension of packed bed reactors in the chemical industries. The first one type of reactor which I will explain is plug flow reactors. First of all, I will show you the definition of plug flow reactors. Defining plug flow reactors, a plug flow reactor is the form of chemical reactor where reactants continuously flow through a tubular system, maintaining a specific concentration profile along the reactor's length. Unlike reactors with thorough mixing, PFRs enable each portion of fluid to undergo distinct reactions conditions as it progresses through the system. Now moving toward the key characteristics of plug flow reactors. Continuous flow. Reactants enter and products exit continuously, ensuring a constant operational state. Axial mixing. Flow predominantly occurs along the reactor's axis, minimizing mixing perpendicular to the flow direction and resulting in a unique concentration profile. Single path. Each fluid element follows an unchanging path through the reactor, contributing to distinct concentration and the temperature profiles. Idealized model. While actually PFRs may have some radial mixing, the ideal PFR model assumes the perfect plug flow without radial mixing of gradients. Design of plug flow reactors. Designing plug flow reactors involves adherence to key principles for optimal performance. Here's a breakdown of these fundamental considerations. Number one, geometric configuration. PFRs are typically configured as elongated straight tubes to facilitate plug flow. This design minimizes radial mixing, preserving distinct concentration profiles along the reactor. Second one, consistent cross-sectional area. Maintaining a uniform cross-sectional area ensures a constant velocity of the reacting fluid. This contributes for achieving consistent residence times for all fluid elements. And there you can see the diagram of plug flow reactors. Number three, material selection. Materials are chosen based on the specific reactions and reactants involved. Considerations include corrosion, resistance, thermal stability, and compatibility with reaction conditions. Number four, temperature management. Precise temperature control mechanisms are integrated into PFR design. Cooling or heating jackets are often employed to sustain optimal temperatures. Number five, resistance time distribution. Narrowing the resistance time distribution is crucial. A uniform resistance time ensures consistent reactions conditions for all reactants, impacting product equality. 6. Inlet and outlet configuration. Careful design of inlet and outlet section minimizes disruptions to flow profiles. Smooth transitions and appropriate geometries are implemented to avoid dead zones and ensure proper fluid distribution. Number 7. Pressure handling. Plug flow reactors must withstand the pressures generated during reactions. Pressure control mechanisms are integrated to manage variations and ensure safety. Number 8. Instrumentation and monitoring. Sensors and monitoring systems are incorporated for real-time tracking of parameters like temperature, pressure, and concentration. This enables ongoing control and adjustments during operation. Number 9, safety measures. Safety features including emergency shutdown system and pressure relief mechanisms are integral to the design. Number 10, scaling considerations. Design accounts for scalability, ensures adaptability for different production scales without compromising efficiency. We should keep these all points in our mind during designing our plug flow reactors. Now we will see the residence time distributions in plug flow reactors. Residence time distribution is a crucial factor for influencing the performance of reactors, including plug flow reactors. uh, Residence time distribution or time that individual fluid elements spend inside the reactor. Here's how residence time distribution impacts reactor's performance. Uniform residence time. An ideal plug flow reactor would have a narrow and uniform residence time distribution. Uniform residence times ensures that all reactants experience similar reaction conditions, promoting consistent product quality. Peak resistance time. The peak of the resistance time distribution curve represents the most probable residence time. For efficient reactor performance, this peak should align all the described reactions for optimal conversion, spread, and dispersion. A wider residence time distribution indicates greater dispersion and the time it takes for different fluid elements to pass through the reactor. Increased dispersion can lead to variations in conversion rates, affecting the overall efficiency of the reactor. Incomplete reactions. Long residence times for some fluids elements may result in overreaction, leading to undesired byproducts or incomplete conversions. Short residence times might cause insufficient reactions, reducing overall yield. Incomplete reaction. Long residence time for some fluid elements may result in overreaction, leading to undesired byproduct incomplete conversions. Effect on reactor design. Residence time distribution influences reactor design considerations. Engineers may implement design modification to achieve a more uniform residence time distribution, such as adjust the reactor length or introducing mixing elements. Back mixing effects. In plug flow reactors, a perfect plug flow implies no back mixing. However, variations in residence time may introduce some degrees of back mixing. Back mixing and impact the concentration profile and affect the overall performance of the reactor. Optimizing reaction conditions. Understanding residence time distribution allows for the optimization of reaction conditions. By controlling flow rates and the reactor dimensions, engineers can tailor the residence time distribution to meet specific reaction requirements. Experimental measurement. This data helps validate reactor models and allows for adjustments to improve the performance. Now I will tell you about the applications of plug flow reactors in chemical industries. Plug flow reactors find applications in various chemical processes where their specific characteristics are advantageous. Here are examples of chemical processes commonly utilizing plug flow reactors. Number 1. Continuous catalytic reactions. Plug flow reactors are commonly used in processes like biodiesel production from triglycerides, ensuring continuous and controlled catalytic reactions. Number 2. Polymerization reactions. Plug flow reactors find application in polymerization process such as continuous production of polyethylene, ensuring controlled and steady polymerization. Number 3, petroleum refining. In petroleum refining, plug flow reactors are employed for specific processes like hydrotreating or hydrocracking, ensuring continuous and controlled reactions. Number 4, pharmaceutical synthesis. Plug flow reactors are utilized in pharmaceuticals manufacturing for specific reactions in drug synthesis, providing precise control over reaction conditions. Number 5. Chemical synthesis of fine chemicals. Fine chemical production process benefit from plug flow reactors, ensuring high purity and controlled reactions conditions. Number 6. Aromatic production. Plug flow reactors are applied in the production of aromatic compounds like benzene or toluene, providing well-defined reaction conditions. Continuous biodiesel production. Trans-esterification reactions in continuous biodiesel production benefit from plug flow reactors, ensuring efficiency and continuous processing. Number 8. Gas-phase reactions. Certain gas-phase reactions such as ammonia synthesis or ethylene oxide production utilize plug flow reactors for precise control over temperature and concentration profiles. Number 9. Oxidation reactions. Plug flow reactors find application in oxidation reactions, including the production of maleic anhydride or adipic acid, ensuring controlled and efficient reactor pathways. Except these applications, there are many numerous applications in chemical industry which are utilizing plug flow reactors. Now we will see the merits of plug flow reactors, their advantages. Number one, high efficiency. Plug flow reactors offer high efficiency due to their continuous and unidirectional flow, allowing for optimal reaction conditions and minimal side reactions. Number second, precise control. The design of plug flow reactors enables precise control over reaction parameters such as residence time and temperature, leading to better control of the reaction kinetics. Uniform residence time. Ideally, plug flow reactors maintain a uniform residence time for all fluid elements, contributing to consistent product quality and yield. Suitable for fast reactions. Plug flow reactors are well suited for fast reactions where maintaining a specific reaction time is crucial for product quality. Easy scale up. Plug flow reactors are relatively straightforward to scale up for industrial processes, making them adaptable for varying production scales. Minimal mixing. Radial mixing is minimal in plug flow reactors, allowing for the preservation of concentration gradients and defined reaction pathways. Now we will see the demerits of plug flow reactors, and we should keep these demerits during using any kind of reactor in chemical industries. Number one, sensitivity to flow rate variations. Plug flow reactors can be sensitive to variations in flow rates, potentially impacting residence time and consequently reactions outcome. Number two, difficulty in heat management. Managing temperature gradients can be challenging in plug flow reactors, especially for exothermic or highly temperature sensitive reactions. Number three, complex design and construction. Designing and constructing plug flow reactors can be complex, especially for large scale industries application requiring careful consideration of reactor length and materials. Number four, limited applicability for slow reaction. Plug flow reactors may not be ideal for slow reactions where longer residence times are required, as the continuous flow may limit the extent of reactions. Number five, potential for channeling. In some cases, channeling or preferential flow paths may occur, leading to uneven residence time distribution and non-ideal reaction conditions. Number seven, safety concerns. Continuous flow and potential for rapid reactions in plug flow reactors can pose safety concerns requiring robust safety measures and control systems. Now I will conclude these plug flow reactors. Plug flow reactors present notable benefits in chemical processes, offering efficiency, precise control over reaction parameters, and adaptability for rapid reactions. Their conditions and one-directional flow facilitates optimal reaction conditions and scalability. Nonetheless, challenges like sensitivity to flow rate variations, heat management complexity, and the potential for channeling need thorough consideration. The decision to imply a plug flow hangs on the specific demands of the chemical processes, emphasizing the importance of controlled and effective reaction pathways. The second type of the reactor I have explained in these articles is fluidized bed reactors. First of all, I will show you the definition of fluidized bed reactors. A fluidized bed reactor is a chemical reactor where a bed of solid particles suspended by the upward flow of gas or liquid exhibit a fluid-like behavior. This dynamic fluidization state improves heat and mass transfer, making fluidized bed reactors applicable for diverse chemical processes including catalytic reactions, combustion, and particle coating. Now, we will see the working principle of fluidized bed reactors. Fluidized bed reactors function by initiating a fluidized state in which solid particles are suspended due to the upward flow of gas or liquid. The process involves the initial compact bed expanding as the fluidizing medium enters from below, creating a dynamic equilibrium. This fluidized state enhances mixings, facilitates efficient heat and mass transfer, and allow for various chemical processes, including catalytic reactions. The reactor's fluidized nature optimizes heat transfer for temperature control and the reaction rates. After completion, products are separated from the fluidized bed, typically using devices like cyclones. Overall, fluidized bed reactors offer advantages such as improved mixing and efficient transfer of heat and mass, making them suitable for diverse chemical reactions. And there you can see the diagram of fluidized bed reactors. Now, I will tell you about the types of fluidization. Fluidization can occur in various forms. Type of fluidization depends upon the flow characteristic of the gas or liquid through the bed of solid particles. Common types include number one, bubbling formation, fluidization. In this formation of distinct gas bubbles in the bed occurs. Random particle movement resembling a boiling liquid also occurs. It is suitable for applications requiring moderate fluidization. Number two, sludging fluidization. It offers intermittent creation of large gas pockets or slugs. Alternate between settled and fully fluidized states and may lead to uneven particle distribution. Number three, turbulent fluidization. It provides high gas velocities, induce intense particle mixing, chaotic motion resembling turbulent fluid behavior, also offers improved mass transfer for demands higher energy input. Number four, circulating fluidization. It gives continuous circulation of particles between the bed and external systems, creating a loop with particles exiting and re-entering the bed. It is ideal for processes requiring continuous removal of the solids. Number five, fast fluidization. It provides higher gas velocity than standard fluidization. Particles exhibit fluid-like behavior with enhanced mixing. It is suited for applications demanding rapid heat and mass transfer. Now we will see the components of fluidized bed reactors. Number one, bed material. Solid particles fluidize by the upward flow of gas or liquid. The selection of bed material depends upon specific reaction needs. Number two, distributor plate. Position and the reactor space. It uniformly disperses the fluidizing medium to ensure consistent fluidization of the bed. Number three, fluidizing medium inlet. Entry point for the gas or liquid creating the fluidized state. The fluidizing medium follow rate and composition are crucial for optimal reactor's performance. Number five, heat exchange system. Manages and regulates the reactor temperature using structures like coils for effective heat transfer. Reaction zone. The area where chemical reactions occur among the fluidized particles crucial for achieving the desired conveyance of reactor. Product outlet. Point for removing reactions. Product separation methods such as cyclones or filters are commonly applied here. Gas outlet. Fluidized bed reactors allows the exit of fluidizing gas after interacting with the bed material. It may lead to further processing or treatment. Pressure control system. Fluidized bed reactors maintain the desired reactor pressure, essential for optimizing reaction conditions and ensure safety. Instrumentation and controls. Monitoring devices, sensors, and control systems that regulate parameters like temperature, pressure, and flow rates for effective reactor operations. Now, I'll tell you about the applications of fluidized bed reactors in different chemical industries. Fluidized bed reactors are versatile and find application across industries for various purposes. Number one, chemical processing. Fluidized bed reactor is employed in a range of chemical reactions, including catalytic processes like hydrocracking and fluidized catalytic cracking in the petroleum refining sector. Number two, petrochemical industry. Fluidized bed reactor is utilized in the production of petrochemicals such as generating olefins through the catalytic cracking of hydrocarbons. Number three, combustion and gasification. Fluidized bed reactor is used for efficient burning of solid fuels in the combustion process and in gasification for production synthesis gas from carbonaceous materials. Number four, biomass conversion. Fluidized reactor is applied in the thermochemical conversion of biomass for producing biofuels and biochemicals. Number 5, pharmaceutical industry. Fluidized reactor is applied in pharmaceutical powder coating, granulation, and drying processes, enabling precise control over particle in size and distribution. Number 6, metallurgical processes. Fluidized reactor is used in metallurgical applications for processes like roasting, calcination, and reduction of ores. Number 7, environmental control. Fluidized reactor is applied in the fluidized bed incinerators for efficient waste combustion and disposal. Number 8, food ready processing. Fluidized reactors is utilized in drying and frying applications, offering a controlled and uniform environment for processed food products. Number 9, cement industry. Fluidized reactor is applied in the production of cement clinker through processes like calcination. Number 10, waste treatment. Fluidized reactor is used in water treatment processes for the removal of contaminants, providing a versatile platform for chemical reactions. Now moving toward the advantages of fluidized bed reactors. Fluidized bed facilitates superior mixing, leading to heightened rates of heat and mass transfer, advantageous for diverse chemical processes. The fluidized state ensures an even temperature distribution within the reactor, minimizing temperature variations and ensuring uniform reaction conditions. Fluidized reactors are adaptable and suitable for a broad spectrum of applications ranging from chemical processing to environmental management and biomass conversion. Enhanced contact between the reactants and catalysts and the fluidized states often result in accelerated reaction rates, improving overall reactor efficiency. Fluidized bed accommodates a range of particle sizes, providing flexibility in choosing bed materials and enabling diverse applications. The fluidized state promotes effective mixing of solid particles, ensuring uniform reaction conditions and preventing particle clumping. Now we will see the disadvantages of fluidized bed reactors. The continual movement of particles in the fluidized bed may lead to wear and attrition impacting the lifespan of catalysts or bed materials. Certain reactions or conditions can cause a particle agglomeration, resulting in uneven fluidization and potential operational challenges. Designing and controlling fluidized bed reactors can be intricate to the factors such as particle dynamics, fluidization regimes, and the need for precise temperature and pressure control. Achieving and maintaining the fluidized state may demand substantial energy input, especially in turbulent or fast fluidization scenarios. High velocity fluidization can lead to erosion of reactor internals, requiring frequent maintenance and part replacement. Scaling up of fluidized bed reactors for large production capacities can be challenging, and issues encountered at smaller scale may not directly translate to larger systems. Now moving toward the case studies. And this we will study that where fluidized bed reactors have recently used for various applications. And these are number 1, catalytic cracking in petroleum refining. A refinery introduced a fluidized bed reactor in fluid catalytic cracking to improve the transformation of dense hydrocarbons into more valuable lighter products. The fluidized bed reactor enhanced heat and mass transfer, resulting in heightened reaction rates and improved overall production efficiency. This led to increased yields of high quality gasoline and diesel. Number 2, biomass gasification for syngas production. A bioenergy plant implemented to a fluidized bed reactor to gasify agriculture residues producing syngas. The fluidized bed ensured a consistent temperature distribution, facilitating effective conversion of biomass and syngas generation. This allowed the facility to generate a sustainable and environmentally friendly energy source for diverse industrial application. Number 3, pharmaceutical powder coating. A pharmaceutical firm incorporated a fluidized bed reactor to apply a polymer film coating on drug particles, aiming for formulations with controlled release. The fluidization bed facilitating even coating, ensuring consistent kinetics in drug release. This led to the creation of pharmaceutical products with enhanced effectiveness, and greater adherence for patients. Now I will conclude the fluidized bed reactors. Fluidized bed reactors are dynamic and versatile assets in chemical engineering, providing superior heat and mass transfer for diverse applications. Their capacity to sustain a fluidized state with particles in suspension allows for enhanced mixing and reaction rates, making them indispensable in processes like catalytic reactions and biomass gasification. As industries seek inventive solutions, FBRs continue to play a crucial role in maximizing efficiency and promoting sustainable practices. And the third type of reactors I have been covered in my article is packed bed reactors. The definition: packed bed reactors are vessels filled with solid particles or catalysts where chemical reactions take place as fluids pass through the packed bed. This design enhances mass and heat transfer, making it valuable in various industrial applications. Now, moving toward the working principle of packed bed reactors. The structure of the packed bed allows for efficient surface contact, making a packed bed reactor versatile for various chemical processes. Additionally, if catalysts are used, packed bed reactors enable their regeneration, extending the reactor's operational life. Packed bed reactors operate by containing a bed of solid particles and catalysts. Fluids, either the gases or liquids, flow through this bed, engaging in chemical reactions on the surface of the solids. The process involves mass and heat transfer, with the reactants moving with the fluid to the solid phase. Packed bed reactors typically maintain continuous flow and careful control of parameters like temperature and pressure ensures optimal reaction conditions. And here you can see the diagram of packed bed reactors. Now I will tell you about the structural elements of packed bed reactors. Packed bed reactors are composed of a cylindrical chamber that houses solid particles or catalysts. The essential components encompass the reactor vessel, the packed bed configuration, and inlet-outlet ports, facilitating fluid flow. The selection and arrangement of packing materials, along with the design of the support structure, play a vital role in determining the reactor's effectiveness. Furthermore, the reactor design may incorporate features of our temperature regulation and monitoring instrument to ensure accurate operation. Types of packing materials and their significance. Packed bed reactors utilize diverse packing materials such as ceramic saddles, metal rings, or specialized catalyst particles. The selection depends upon factors like surface area, porosity, and catalytic activity. The importance lies in the maximizing interaction between the packing and the fluid, facilitating effective mass transfer and improving the overall reaction rate in the reactor. Flow distribution and pressure drop consideration in packed bed reactors. In packed bed reactors, it's vital to carefully consider how the flow is distributed and monitor pressure drops, ensuring even flow across the packed bed materials, maintain consistent reaction rate, while keeping an eye on pressure drop helps evaluate fluid flow resistance, maintaining uniform flow distribution prevents concentration variations in specific areas, improving the reactor's overall efficiency. Fluid-solid interaction in packed bed reactors. Here are some important factors which are crucial for fluid-solid interaction in packed bed reactors. Number one, explanation of how reactants interact with solid catalyst particles. Reactants interact with solid catalyst particles in packed bed reactors through surface reactions. As the fluid containing the reactants pass through the packed bed, the reactant molecules come into contact with the catalyst surface. This contact facilitates chemical reactions where bonds are formed to broken on the catalyst active side. The solid catalyst provides a platform for the reaction to occur, influencing the reaction pathway and accelerating the overall process. Efficient interaction between the reactants and the catalyst surface is essential for achieving high reaction rates and optimizing the reactor performance. Moving toward the applications of packed bed reactors. Packed bed reactors have diverse applications in industries such as petrochemicals, pharmaceuticals, environmental engineering, chemical manufacturing, food production, biochemical engineering, hydrogen production, and polymerization reactions. They play a crucial role in the processes like catalytic cracking, drug synthesis, air and water treatment, ammonia and hydrogen production, enzymatic reactions, fermentation, and polymerization. The adaptability of packed bed reactors makes them essential in various contexts requiring controlled chemical reactions. Now, I will tell you about the advantages of packed bed reactors, which make them useful in the chemical industries. Number one, ample surface area. Packed bed reactors provide extensive surface area, fostering effective interaction between reactants and catalysts, enhanced heat and mass transfer. The packed bed configuration facilitates improved heat and mass transfer, leading to heightened reaction rates. Continuous separation. Packed bed reactors operate continuously, ensuring a consistent production flow. Catalyst renewal. Packed bed reactors enable the renewal of catalysts, prolonging the reactor's functional life. Moving toward the disadvantages of packed bed reactors. Number one, pressure drop challenges. Elevated pressure drop may impact fluid flow, demanding careful consideration during reactor's design. Potential clogging. There's a risk of bed clogging due to falling or particle deposition, potentially affecting reactor's efficiency. Temperature variations. Uneven temperature distributions within the packed bed could result in localized hot spots or cold spots. Now, I will tell you about the case studies. In this, we will see where recently packed bed reactors have been used. And their uses are number one, methanol synthesis. Packed bed reactors utilized for large-scale methanol production from carbon monoxide and hydrogen. Investigate reactor design, optimizations, and economic feasibility. Catalytic conversion on a packed bed of copper, zinc oxide, aluminum oxide pellets. Number two, water treatment via catalytic oxidation. Packed bed reactors applied in catalytic wet air oxidation for water treatment. Focus on pollutants removing using a noble metal catalyst in packed bed. Evaluates efficiency, reactor stability, and environmental impact. Biological wastewater treatment. Packed bed reactors adapted for biological wastewater treatments with immobilized microorganisms, examines efficiency in nutrient and removal and impact on microbial activity, addresses reactor stability in the treatment of industrial wastewater. And here's the conclusion of packed bed reactors. Packed bed reactors are pivotal in the chemical processes, providing benefits like extensive surface area, effective mass transfer, and adaptability in diverse applications. Despite challenges such as pressure drops and potential clogging, their role in sports continuous operations and enabling catalyst regeneration underscores their importance in various industry settings. Ongoing technical advancements and research enhance their relevance in the optimizing reactions across the different industries. And at the last, there are references I have been used for making these articles. I hope these all types of reactors are clear to you and this article is really helpful to you. Stay safe and stay happily. Allah Hafiz.